All right, guys. So welcome back to supposed to be the second half of this morning's lesson. Okay, with limits. Um, I took the liberty of graphing, and I meant to highlight this. This I graphed it. Okay, because we're going to use it. We're going to evaluate the limit by graphing initially. Okay. Um, the other thing we're going to do here, okay, is I want to plot. I actually want to plot this graph here, which we can do in yellow. That's no problem. Okay. So what I want to do here, but the catch here, just careful to the boundary on it. Okay. I ultimately want to find out, does this limit exist, right? Or is the graph continuous as x approaches -2? That's ultimately what we're after. Okay. And remember, a function is continuous if there's no breaks in its graph. Okay. So I'm going to plot the 2x plus 4, right? So you guys, I'm okay with this, and you guys might choose to do this too. This helps me anyway. I'm just going to plot this like a normal line, and then I'm going to erase all the x value points that fall outside of this. Okay, so I'm just going to go up to +4. 1, 2, 3, 4. I'm going to plot a point there, and I'm not really interested in going in this direction because I'm interested in all of the x values that are less than -2. So I'm just going to go, the slope here would have been up to right 1, right? But I'm interested in, so if I'm going to continue this line, I'm going to go down to left 1. Down to left 1, okay? Down to left 1. Now here's the catch. They've said, so we've kind of got our pattern. We know what's going on, so we can erase these points here. We don't need these anymore, okay? Now the catch here is, you know, at 2 here, it's x less than -2, not less than or equal. So that means that there's a hole there, okay? And I'm just going to continue graphing this here for a second. I'm just going to keep going, right? And when we say like this, okay, so here's our what we call a piecewise function. Okay, it's got two pieces in this instance, okay? Now, we need to make the decision around, you know, what's going on, like graphically. Is this graph continuous, right? Particularly around the limit as x approaches -2, right? Well, it turns out if you were to ever have a hole like what we have here, right? And holes exist because we don't actually include the x value. It's not equal to, less than or equal. So if you ever have a hole, and then on top of that, the point actually, like we have a point on top of that hole as well, the point actually knocks that hole out. Okay, so we actually get just the point, and the graph is actually continuous there, right? So I can actually fill in this hole with the point, and it tells me that it's continuous. Okay, so we know graphically, no problem, right? And sometimes it's easy to see right off the graph that something's continuous versus is not continuous, right? So we know f of x is continuous based on the graph. Okay, and it's continuous for all x er. All x, any numbers are part of the real, any x values are part of the real numbers. Okay, so that's what's nice about the graphs. You can visually see that, right? Whereas if we were to do the algebra, I mean, the algebra is good too, right? You just evaluate on both sides of the limit, right? So I'm going to see what's happening on the left side of x equals -2, and I'm going to see what happens on the right side of -2. Okay, so we're just going to evaluate the two limits as x approaches -2 from the left, right, of the function. And we could denote this as being the left side limit so that you're very clear, right? So the left side limit will be the limit as x approaches -2 from the left of, and which one should we do? Well, the graph on the left side, right? Remember, our point of interest is going to be this x equals 2 value. Don't confuse that with an a vertical asymptote. Sorry, I'm just drawing this here for your reference. Okay, there's 2 there. So the left side of that graph is the yellow portion. So that's the piece that I'm going to evaluate at, right? So I'm going to see what I'm going to see what happens when I check -2, right? So the limit, we don't even need the limit because we're going to evaluate now. We're going to get, don't forget your equal signs, and then 2 times -2 plus 4, well, that's going to equal 0. Okay, and then if we jump over and we check the right side of the limit, I'm going to check the limit as x approaches 2 from the right. Well, that's the blue graph, right? So the blue graph is on the right side of our where we're actually checking the limit at x equals 2, or as x approaches -2, sorry, not 2. And so we're going to see f, you're checking this limit, right? Okay, well, if we're using the blue graph, then we're going to check the limit as x approaches 2 from the right of 4 minus x squared. So what happens? Well, we get 4 minus 2 squared. And now we see algebraically that the left side limit equals the right side limit, which means this graph must be continuous. Okay, and the limit exists. You could also say that too, right? An S on there, okay? So that's that, right? Like, we do these things in 2 stages, right? And sometimes I think the graphing, especially with the piecewise functions, is like, it's an important part of actually visually representing what you see, right? And so we're just going to do a few more of these. We'll get a few of these questions done up here, okay? So we're just going to have a run through them, okay? So let's just have a look at this function here. I didn't have a chance to actually plot this one, but why don't we start with the top one, right? So we're looking at, okay, well, we got a line there, right? -x plus 3. So why don't we plot that? Right, and it's we can plot it, and then we can adjust what it is that we are actually looking at by erasing some of the points, right? So let's just plot this as if it's a normal line, and then we will erase some of the points that are not in this boundary, or that do not fit this condition of x is greater than or equal to 1. Okay, so let's plot. We know the graph starting here at +3, and the slope is -1. Right, so we're going to do something like this. Okay, so there's our graph. Okay, now here's the catch. I shouldn't have drawn the line yet. I only want x values that are greater than or equal to x equals 1. So I'm going to erase that initial one, sorry, and then I'm going to draw this. Oh boy, that might not work. Oh, there we go. Okay, so there's the first part of this. And then we have to plot the second part, right? And so we want to see, okay, well, what does x cubed look like? Well, x cubed would follow a pattern of something that has to go through the origin. And then if I were to cube an input of x equals 1, I would get 1. Okay, and then I would get -1 if I cubed that, -1. And then if I cube -2, right, I'll get -8. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so there's kind of that graph. Now here's the catch though. Not x is less than or equal to 1. It's just less than 1. Right, which means that this point here at x equals 1, or for an x value of 1, I have a hole. Okay. These are kind of fun questions from the standpoint that you get to like create kind of cool graphs, right? Now you guys get to see here. You don't have to do this. I don't know. I do this for my own personal reference, and this is just something I'm doing on the fly here to help me in something that I've never done, but something I haven't done in a while, right? So this is helping me illustrate to myself, right? It's very clear. Well, we can right off the bat we can see that this is not continuous, right? Because there's a jump when x equals x equals 1, right? And so the function itself, g of x, is not continuous as a result, okay? Because of this jump, right? Or discontinuity, we could say. Okay, so we'll just leave it at that. Okay, now why I draw this line is the line actually helps me quite a bit in terms of, okay, well, I'm interested in x values greater than 1. Which part of the graph am I using? Well, the side on the graph on the right. And you might choose not to do this as you get the hang of doing more of these questions, right? But as I go to check this algebraically, I have to know which side is what. Okay? So we know that from the graph that this is not, and you could erase that after, it's just helping me, right? It looks like the reason why I have an issue with it is it kind of looks like a vertical asymptote, and it's not, okay? And people will have an issue with that. It's just helping me visualize and come up with which part of the graph is the left side limit and which part is the right side limit, okay? So we're gonna check both of these as the limit of g of x approaches x equals 1. So the limit as x approaches 1 of g of x, right? That's what I'm checking. So on the left side, I'm dealing with the blue function. Okay, so I'm going to say, okay, well, we're going to evaluate the limit as x approaches 1 of x cubed. Okay, and we're going to see that we get 1. I should say 1 from the left, sorry. Be more specific. If you're coming from the left side, denote that you're coming from the left side, okay? And then the right side, we're going to use the yellow graph. Okay, we're going to check what the limit is. So we're going to check the limit as x approaches 1 from the right of g of x. Right, and so that's going to equal the limit as x approaches 1 from the right of negative x plus 3. Okay, so we just evaluate with the direct substitution. We get negative 1 plus 3, which will equal 2. And you can see that the left side limit does not equal the right side limit, and therefore not continuous. Okay, or the limit, you should also say that the continuity is kind of this afternoon's portion of the lesson. We're going to actually discuss that, but like we're going to say that the limit does not exist. These two things go hand in hand, okay? And we're going to spend a little bit of time this afternoon just dealing with the continuity aspect of functions, okay?